Thank you for inviting me, and thank you all for coming. So I'm going to start off talking about a famous problem, the P versus NP problem. And it's probably one of the most famous problems in, can you hear me? Yes. It's one of the most famous problems in mathematics, and this is proof that it's even made its way into popular culture, debuted. You can hardly see it, but it's got its debut here on The Simpsons, where I guess Homer thinks P equals NP. And here he is trying to solve or pondering the clique problem. Given a graph on n vertices, does it contain a clique of size, say, n over 2? And a clique is a subset of the vertices of that size where every edge is present. So in that graph, it does have a clique of size 3. We now know from seminal work from the 70s due to Cook and Levin and Karp and others that this is a very rich problem, and there's thousands of NP-complete problems, and they're all equivalent in the sense that P equals NP if and only if any one of these NP-complete problems has a polynomial time solution. So in particular, to study the P versus NP question, we just have to understand if the clique problem can be solved in polynomial time. And I like a paper that Christos wrote a while back where he described the NP completeness problem, perfect timing. He described the NP completeness problem, and he gave a bunch of reasons for why it's so important. And my favorite one was it's used allegorically, I think I have his terminology right, to sort of understand the difference between difficulty and easy. And it's not just in computer science and mathematics, but in all areas, in many different areas of science. It's used this way. So anyways, it's an important concept, and it's the basic question behind a lot of what people do in complexity theory. And the reason I have this picture up here, this is from the Globe and Mail. There was an article on the P versus NP problem a few years ago in the paper. And the reason I have this slide up here, aside from the fact that Steve has a different answer than Homer, is that on the left here, there's a picture of a Boolean circuit. And indeed, Boolean circuits is the most common model that's around for studying the P versus NP problem. So Boolean circuit model is a non-uniform model of computation, and that means you have a separate circuit or a separate program for every input length. So for the clique problem, for example, you have to first of all Booleanize your input. So for graphs on n vertices, you can represent the input. You can look at the adjacency matrix of the graph, and you'd have n squared variables, where a variable xij would tell you whether or not vertex I is connected to vertex j in the graph. Okay, so you have n squared Boolean variables. And the inputs to the circuit would be those Boolean variables or the negation of those Boolean variables. And the internal nodes of the circuit are Boolean gates or an AND. And it computes a function in the obvious way. Given a 0, 1 value for the input to the circuit, you just bubble up evaluating the intermediate gates until you get an answer. Okay? And to prove P not equal NP in this model, you have to show that for sufficiently large n, that there's no circuit of size polynomial in n that computes the clique function. Okay? So for example, you have to rule out circuits of size, all circuits of size, say n to the 5th, or n to the 100th, or n to the 1,000,000th, for solving the clique problem on n vertices. So why did we switch to circuit complexity? I'm going to keep this brief, but there's a lot of reasons for really loving this model. First of all, it does solve the problem. So superpolynomial circuit lower bounds does imply P not equal NP. And secondly, because you have a different algorithm, so to speak, for each input length, you can study the complexity of finite functions. So you can really study whether you can compute the clique problem on n equal 1,000,000 vertices. You can study, can you factor numbers of length up to 3,000? And those are interesting questions in their own right. Even if the clique problem can't be solved in polynomial time for all n, we really might, the world is finite. So it matters what happens for large but finite values of n. And then two other reasons that are deeper, and I'm not going to explain the proofs today, for what's interesting about circuit complexity. The third reason here is more or less saying that in some sense, studying the circuit complexity of NP-complete problems is a win-win situation. So if you prove a lower bound, a strong enough lower bound for the clique function, you're proving P not equal NP. And it turns out that if you can prove good enough upper bounds, so if you can show that all languages that have exponential time algorithms, if you can show that all of those languages actually can all be done with polynomial size circuits, that's another way to prove P not equal NP. So this is sort of surprising. So upper bounds imply P not equal NP, certain upper bounds, and obviously lower bounds do. And lastly, circuit complexity lower bounds are very closely connected to the question of de-randomization. So that's the question of, given an arbitrary polynomial time algorithm that can flip coins, can you de-randomize it? And that's a fascinating question that complexity theory has been studying for the last 20 or 30 years. And we now know that it's very, very closely connected to proving certain circuit lower bounds. Okay, so short, brief history of time. We had some fabulous results in the 80s. Two notable ones are monotone circuit bounds for the clique function by Razborov. And a monotone circuit is a circuit with the restriction that the inputs have to be just positive. So you can't have any negated variables. Okay? And if you're computing a monotone function such as clique, it's okay. You can study this model because monotone circuits can compute monotone functions. And Razborov proved that really elegant proof that there are no sub-exponential size circuits for the clique function. So in a sense, monotone P doesn't equal NP. Okay? And roughly around the same decade, another restriction of the problem was solved, the AC0 circuit lower bound problem. AC0 circuits are, again, Boolean circuits. Now you're allowed to have negations, and the restriction here is the depth of the circuit. So the length of the longest path from the output to the input is bounded. And these were some great results. There's others. I'm just pointing out these two. I think they're two of the more famous ones. Since then, we don't know how to prove P not equal NP. Since then, people have identified some really some subproblems that in and of themselves are really great subproblems, interesting in their own right. And you have to solve these subproblems in order to prove superpolynomial circuit lower bounds. And I'll tell you more about these later, but what I want to talk about today is information complexity and communication complexity, and I want to explain to you how you can attack all of these problems using tools from information complexity. And I'll leave it a surprise which ones have already been proven using information complexity and which ones we have a setup, a framework, an information complexity framework, but it has yet to be carried out. Okay? Okay, so what I want to tell you about today is introduce these beautiful topics of communication complexity and information complexity. It's a rich combinatorial framework. It's very easy to understand. There's some really intrinsically interesting open problems in the model. And like I said on the last slide, it's a very powerful tool for proving lower bounds. All of those three major subproblems can be solved using certain techniques from using communication complexity. And at the end, I'll tell you about other applications outside of lower bounds, on the way toward P not equal NP. There's a huge array of applications for communication complexity, and so I'll touch on those at the end. If you have any questions, feel free to interrupt me, by the way. Okay, so it starts really with a classical, probably one of the most influential papers of all time, Shannon's 1948 paper called A Mathematical Theory of Communication. And in this paper, as you probably know, he defines the famous entropy function, which intuitively is how much information is contained in a random variable x. And we now know that it's more or less equal to the least number of bits that are required to transmit a random element from x. Now, communication complexity in one sentence is more or less the generalization of this transmission problem setup to the interactive setting. So in Shannon's case, messages were sent, somebody had a message and they sent it. And in this case, we're going to have an interactive version of that. So I'll start with the simplest model, the two-player model of communication complexity defined by Yao in '79. And we'll start with the deterministic version, which is the simplest. So you have these two players, Alice. This is her on the left. She looks just like Bob, but anyways, that's Alice. And that's Bob on the right. And they each hold an n-bit Boolean string. Okay? And again, when you want to use this model to compute a function, you want to think of a family of protocols, one for every n. Okay? So they each hold an n-bit string, and their goal is to compute some function f, a joint function of their inputs x and y. And usually you want to think about this function as being Boolean, or at least you want to think about the range of this function as being much smaller than the domain. Okay? So one thing I want to point out is one difference between the previous slide and this one is now we're interested in computing a function of the inputs instead of just sending the message. That's sort of necessary because if all you wanted to do was send your inputs, there would be no interaction needed. So we're generalizing it in two ways. We're going to talk about an interactive version, and we're also going to generalize it so that they each have a bunch of data, but they don't want to send necessarily all of it, but they want to, learn. They each want to learn some interesting bit of information about their inputs. Okay, so a protocol is basically an interaction between them. They have some fixed agreed upon protocol that involves somebody starting. Alice starts, she sends a bit. Then Bob responds with a bit, and they continue in this way until eventually the last message that's sent by the protocol should be the output, the value of the function on xy. And the complexity of the protocol will measure it to be the total number of bits that have to be sent. Okay? And the complexity is the worst case number of bits, the maximum number of bits over all inputs of length n. Okay? And then you can define the complexity of a function to be you look at the best protocol, so the protocol that gets the smallest communication complexity, and that's the complexity of the function. Okay? All right, so I want to look in a little more combinatorial detail at what happens when you run a protocol. This is informal. When you run a protocol to compute a function. And to do this, we have to look at the communication matrix associated with a function. So this is a matrix, M sub f, and all it is a description of the function that they're trying to compute. So here n is 3. Alice has an n-bit string, and on the rows are labeled with all possible 2 to the n inputs for Alice, and the columns are labeled with all 2 to the n inputs to Bob. And an entry like this one, ij, is just the value of the function on this input and this input. Okay. So this is the communication matrix associated with the function. And what we want to see is what happens when you run a protocol. And we want to see that what happens is this matrix is going to get partitioned into pieces called rectangles. And what's a rectangle? So look on the bottom here. A rectangle is a special type of subset of this matrix of the form A cross B, where A is a subset of Alice's inputs, and B is a subset of Bob's inputs. Okay, and we'll see that when you run a protocol, a deterministic protocol, it's going to partition this matrix into subrectangles, and then they're going to be further partitioned into subrectangles until finally you end up with a partition into subrectangles where every single one has the same value. So it's called monochromatic. And then you know you're done and you can give that answer. So let's run this protocol. Bob here, he's the first person that speaks. So he looks at his input. He is one of those y's, and basically he partitions his input into two pieces, whether or not he wants to send 1 or whether or not he wants to send 0. So in this case, on his first 2 inputs, he would send 1, and on the other 6 inputs, he would send 0. Okay? That partitions the matrix into 2 rectangles. And now on this side, when it's Alice's turn, she can see that Bob sent the 1, so she knows that she's working within this left subrectangle. So now she, looking at her inputs, partitions that subrectangle into 2 pieces. So say like that. So on the top 5, she would send a 1, and on the bottom 3, she sends a 0. So that further partitions it into those 2 subrectangles. And now you can see on the top one, the value is always 1. So here she's done. She can announce the answer 1. Okay? And likewise on this path here, this is the subrectangle associated with this leaf. She's also done because this is 0 monochromatic, so she can announce the answer 0. Okay, so you just continue in this way, partitioning. Bob speaks next. He partitions the other side, and something's wrong here. Yeah. In any case, when they finally finish, like I said, you end up with a partition of the matrix into monochromatic subrectangles. Each one corresponds to a leaf in this protocol tree. Okay. And therefore, the number of leaves of the protocol tree is equal to the number of subrectangles. Okay? And you might remember the communication complexity of the protocol was defined to be the maximum number of bits that are sent. So that's the height of this protocol tree. Okay? So because of that, it's easy to see that the communication complexity has to be at least as big as the log of the number of subrectangles induced by the protocol. And it's not obvious, but the other direction is also true. So this thing, what I wrote on the bottom, points out that the communication complexity can be lower bounded by the number of, if you start with a matrix and you know that every way of partitioning it, the only way to partition it into monochromatic subrectangles is big, that'll give you a lower bound on communication complexity. But the other direction is also true. So these two concepts are more or less within small factors that are their equivalents. So if you have a partition of a matrix into subrectangles, you can come up with a small protocol for it. Okay. So that's why I'm going to show you this picture. This complexity class P to the CC, this is the communication complexity analog of the class polynomial time. And it's the set of all functions, f on xy, that have efficient protocols. And efficient here is polylogarithmic in n. Okay? And that corresponds to those matrices that can be partitioned into quasi-polynomial many monochromatic subrectangles. Okay, so this is sort of the visualization of what a function looks like that's in P. Okay? And I just want to point out one thing before I forget. The beauty of communication complexity is that it's really just about messages, information. There's no notion of polynomial time. There's no notion of computation. The players are completely computationally unbounded. So Alice can look at her, when they decide on a protocol and Alice decides whether to send 0 or 1, she can do something that's incredibly difficult. She can run in double, triple exponential time. Doesn't matter. Okay? So there's no computational bounds. That's what's so beautiful about the model, and that's what is going to enable us to prove lower bounds. Okay, so this is the class P, and let me just give you some examples to be a little more concrete. So this is a very simple function. It has very short protocols. The parity function. So now we just want to, remember, x is an n-bit 0-1 string, y is an n-bit 0-1 string, and they just want to output whether the total number of ones is even or odd. Okay, and it's easy because Alice would just compute whether the number of ones is even or odd, send that to Bob, and then Bob just adds that answer to his mod 2 counts. So it's a 2-bit protocol, so it's easy. It's in the class P to the CC. Okay? And now let's look at the equality function. Equality function x, the equality of xy is 1 exactly when these two Boolean strings are exactly equal. Okay? And it turns out this is very hard in the deterministic model. And to show you this, I just want to convince you that the communication complexity is always bigger than the log of the rank over the reals of the communication matrix associated with the function. I don't know what happened there. Where did it go? There we go. Okay, and again, it's just because of this partitioning property. So we said before that if you have a small protocol, then you have a small partition of the matrix into monochromatic subrectangles. So that means you can write the matrix as the sum of all the 1 monochromatic rectangles. And each of the 1 monochromatic rectangles has rank 1. Okay, so that means the total rank of the matrix can't be more than exponential in the communication complexity. Okay? And so because of that, it's trivial to see that equality is hard, because equality corresponds to the identity matrix, which has full rank. Okay, so far so good. Unfortunately, this model is not that strong. It can't even do equality. So we need a stronger version. Oh, sorry. I wanted to tell you about the log rank conjecture. So the rank lower bounds the communication complexity. And a really interesting conjecture by Lovash and Sachs called the log rank conjecture is the conjecture that they're more or less equal. So that the communication complexity is polynomially related to the log of the rank. Okay, so that's the yes. Yeah, so I don't know how far back I should go, but so we saw that if you have a small protocol, then you have a partition into monochromatic rectangles. So take all the 1 rectangles, and that's what this is. This is a picture of one of the 1 rectangles. Okay, and if you add them all up, you'll get this matrix. Okay, and each of these is a rank 1 matrix. So that means that the rank of the matrix is upper bounded by the number of 1 monochromatic rectangles, which is less than the total number of. Okay, so anyways, the log rank conjecture, that's a beautiful conjecture that's still pretty well wide open. asserts that the communication complexity is essentially fully characterized by just understanding the rank of the matrix. So said in simple terms, that's what it's stating. That if you want to understand the communication complexity deterministic of your function, all you have to do is understand the rank. And this is really open. The best record so far was a recent paper by Shahar Lovett, and he shows that the communication complexity is at most roughly square root of the rank. But that's quite far away from log of rank. So I think it's a great problem. Okay, now I want to move on to questions? No. Okay, so now I want to move on to randomized communication complexity. So it's the same as before, but now we're going to, intuitively, we want the players to be allowed to make some mistakes. So we're going to allow them random coins. So they're going to share a random string R, okay? And once they have that shared random string R, then they just run some deterministic protocol. And now what we require is that for every xy, the probability that they give the right answer over the random strings R should be high, like 99 over 100 or 9 over 10. Okay? The complexity is measured the same as before. And this is the picture corresponding to the class of functions that you could solve efficiently in randomized polynomial time. So it's a bunch of protocols. So it looks like a deck of cards. And each one gives you a partition of the matrix into pieces. But now, of course, they might not all be monochromatic. And you're taking the average with, for every xy, the value that you're going to give it, the probability that you get it right is going to be, how many entries in the deck get the right answer. Okay, so now we can go back to equality, and I can show you that equality, even though it was very hard deterministic, is very easy randomized. So this is an example of an x. This is an example of a y. We want to know if they're equal. I'm sure you can see that they're not equal. What the protocol will do, given a random string R, is it'll view R as selecting certain indices of 1 through n. In this case, it selects 3, 4, 6, and whatever the last one is. Okay? And the players, each player, given R, it computes the mod 2 sum of the indices that are pointed to by R. So x is going to compute the mod 2 sum of 0, 1, 1, 1, which is odd. And y will compute the mod 2 sum of 1, 1, 0, 0, which is even. They'll send that bit to the other one, and they say yes, that they're equal exactly if the parity check works out. Okay? So you can see that if they're equal, the parity check will always work out, and it's not very difficult to show that if they're not equal, with probability roughly a half, this parity check will find the mistake. Okay. So it's very easy randomized. It's a constant bit protocol. So what's hard for randomized? The set intersection problem we'll see is hard. And this is the most famous problem in communication complexity. It's the equivalent. It has the equivalent stature that satisfiability has in the real world. This is the version of satisfiability in the communication world. Okay, and the problem is just you're given x and y. Think of x and y as subsets of n, and you want to know if those sets intersect. Okay, so more specifically, is there an index I where xi and yi are both 1? Okay, so this problem we'll see it's very hard randomized. And what's interesting about it is I'm not going to define non-deterministic complexity, but it's easy non-deterministically. So in the sense of the players, if you give them, they're short witnesses. If I give them the value I, or if they guess the value I, it's very easy for them to check that the strings, that they do intersect by just checking that ith bit. Okay? So that's why intuitively this function plays the same role of satisfiability in the communication world. And that's why it's such an important function. In almost all the applications, however many of them there are, spanning lots of different areas, almost all of them, if you just know that this function's hard in randomized complexity, you're good to go with the applications. So if you take one thing out of this talk, besides that p doesn't equal np, take out of the talk that this is a very important function. Okay, in order to prove lower bounds for set intersection, it's useful to use this equivalent definition of randomized complexity. And the equivalent definition uses von Neumann minimax theorem to change the quantifier order. So here, instead of having a random string, there's a distribution mu over their inputs. Okay? And the goal now is to compute fxy with a deterministic protocol with probability, say, 9/10 with respect to this distribution mu. Okay? And the theorem, which like I said, uses this minimax, is that f is easy to compute. F is in BPP. If and only if for every distribution mu, there's a deterministic protocol of cos polylog n. Okay? This definition is easier to use if you're trying to prove lower bounds, and the original definition is the right one to use if you're trying to prove upper bounds. Okay? So it's easier to construct a hard distribution and then prove a deterministic lower bound. Okay, so in order to prove this lower bound for set intersection, there's a very long history of really fascinating papers on it. The first paper was due to Kalyana Sundaram and Schnitger, and it did not use information complexity, which I'll tell you about in a minute. And then that was a hard, quite a difficult, complicated argument. It was simplified by Razbarov, again, not using information complexity. But the most beautiful proof that I know of is the one by BJKS that's maybe 10 years old by now. Anybody remember? And this proof uses this notion of information complexity, which is another way to measure the complexity of a protocol. Okay, so what is information complexity? Again, it's a measure of complexity of a protocol. So instead of measuring number of bits that are transmitted, intuitively we're going to measure the amount of information that the transcript reveals about the player's inputs to each other. Okay? So recall mutual information between two random variables is the average amount of information that B reveals about A, or equivalently that A reveals about B. And the information cost of a protocol P, a communication protocol P, with respect to a distribution mu on their inputs, is the sum of the mutual information between X and the transcript. So intuitively, this is the amount of information that Bob learns from the transcript about X. Okay? Plus the other way around, the amount of information that Alice learns about Y from the transcript. Okay, so this is just a great idea to it might not be obvious to you now, but to define this measure of information. So instead of measuring bits, we're going to look at, well, in order to compute this function, disjointness or whatever it is, how much information do I have to reveal to you about my input? Do I have to send you the whole thing? Can I just send you a couple of bits? And it really is an essential measure. Okay. And it's not hard to see that information complexity, if you get lower bounds on information complexity, it immediately gives you lower bounds on randomized communication. Because if you have a randomized communication protocol that sends B bits, you couldn't have revealed more than B bits of information about X plus Y. Okay? So it's a seemingly stronger notion. And using this measure, that's the third set of authors here proved this result. So why am I highlighting this? This information complexity. Well, first of all, like I said, I think it's just very natural. It's the measure that generalizes Shannon's, concept of transmission. And like I said before, I think that the proof for set intersection, which came after some quite difficult proofs, I think this proof is sort of the textbook proof. It's beautiful, and it uses, in a very natural way, just the properties of information that that are so helpful. So at the core of the argument is a reduction from the n-bit intersection problem to the one-bit and problem, and that uses the chain rule. And the other nice thing about the approach is that you can actually get an exact, with a lot of work, you can get an exact constant. So we know now, that the community knows because of this paper, that for set intersection, that the amount of information that has to be revealed is exactly this number, 0.4827n. And so other work kind of did other things. So there's now been an explosion of research papers using information complexity to prove new lower bounds in communication complexity. And basically, a lot of stuff that was difficult before, that we were struggling with, now has become much easier. So somehow it's the right generalization in a lot of settings that makes previous proofs easier and enables us to prove new things that we weren't able to prove before. On the other hand, there's a paper that came out a few years ago that basically showed that all of the lower bound methods that we currently have for proving natural lower bounds, that all of them are already strong enough to yield information complexity lower bounds. So it's an interesting situation. If we had directly studied information complexity, the proof gets easier, but by not doing so, we sort of tied our hands behind our back, used techniques that were already strong enough, but somehow made life more difficult for ourselves. So this brings up another interesting question, open problem. Are they the same? So we know that if you have lower bounds on information complexity, it automatically gives you lower bounds on randomized communication complexity. But what about the other way around? If you have lower bounds on randomized communication complexity, does that give you information complexity lower bounds? Or said in a better way, if you have a protocol that has low information, can you compress it to get a protocol that doesn't chatter on and on? Okay, can you compress it to just be sending the number of bits that's proportional to the information that you're revealing? And this theorem from a few years ago is basically saying that the answer in some sense is no. So there's a function on n bits and a distribution mu that requires exponential in k communication, but the information complexity is only k. Okay? So I think this is philosophically extremely interesting. It's really, it's basically saying that sometimes if you want to do something and keep the information cost low, you have to chatter on and on and on. And it's really surprising, I think. Just the caveat is that the k, the k is actually a very small number, log n. So it's not the interesting range of parameters that we want for the applications. And it's open to improve this for a function f for all distributions mu. It's also open to improve this to a bigger k. Okay, so in the remaining time, I want to tell you about applications. And I'll first start off by telling you about the promised ones. So I don't know if I'll have time to do all three of these, but I'll tell you at least about two of them, and then I'll give you a quick summary of applications outside of complexity theory. Well, still in computer science, most of them, but outside of circuit complexity. Okay, so the first subproblem is to prove lower bounds for linear programs. So what do I mean by this? Linear programs are one of the broadest class of polynomial time algorithms used to solve all sorts of optimization problems. And we'd like to at least be able to say that there's no linear program for solving clique. Okay? Rule out all linear programs. Technically speaking, if you could do that, you would be proving p not equal np. So you have to define what you mean by a linear program. And Yannakakis had defined, it's a beautiful definition of a very large class of linear programs that he calls extended formulations. And let me just, first of all, give you a little bit of background before I define extended formulations. But I don't know if this story is true. Maybe Christos can verify. But what I heard is that what happened and what led to Yannakakis' paper was that he had been getting all sorts of papers to review that claimed that p equal np, and essentially all of them were very fancy linear programs, and he would have to debug them and find the mistake. And so he once and for all, debunked them all with this paper. Is that a fact?
As true as these stories get, yes.
It's a great story, and it's even true. Okay, so how does one try to prove p equal np? Well, if you want to prove p equal np with a linear program, you start off with your favorite np-complete problem, say traveling salesman. And what do? Well, you try to solve it by minimizing some linear objective function that depends on your instance, subject to lying in the TSP polytope. What's the TSP polytope? It's just the convex hull of all possible solutions. So we have a graph on n vertices. We want to know what's the smallest tour through the graph that travels, that hits all the cities. What are all the possible solutions? They're all possible tours. Okay? So we have this huge high-dimensional polytope that's the convex hull of these solutions. And we just want to minimize some linear objective function that involves our actual instance subject to being in this polytope. So the problem is that the TSP polytope is enormous. It has exponentially many facets. So if you were to write down all the inequalities corresponding to the polytope, you'd have an exponential size in n, linear program, no good. So instead what you do, this is what an extended formulation is, you introduce new variables. You don't just stick with your original variables. You introduce new ones, and you try to write down the polytope using the new variables more succinctly. And if you can do that, you've proved p equal np. Okay? Now, just a caveat, I'm describing a particular large family of linear programs, not every linear program. But I think it's fair to say that we don't, almost every linear program that we know of, this is the way it goes. So what's the reason that this characterization is not fully general is the polytope is defined independent of the instance. Okay? So the instance is only in the in the objective function that you're trying to minimize or maximize over. Okay, so in a picture, so you start off with a polytope P defined by AX less than or equal to B. X is your variables is x1 through xn, that's x. Okay, it defines this polytope P down here. Of course, it's a high-dimensional polytope. I couldn't really show you that, so this is some high-dimensional polytope. And an extended formulation of the polytope P is another bunch of inequalities, EX plus FY equals G, Y bigger than or equal to 0. And that defines a polytope up here in more dimensions. And it's an extended formulation if essentially it projects down to exactly P. So when you project down to the X variables, you're right back to P. Okay? And the extension complexity of this original polytope down here is the minimum size of an extended formulation. And size can be measured to be the number of new variables, these Y variables, that you have to introduce. Okay? The minimum number. Okay. So what Yannakakis did in 1990, this is brilliant, is you start with this ugly, in my opinion, geometric parameter extension complexity of a polytope. How are you going to study that? And he showed that it's equivalent to a very nice linear algebraic notion, which is just the non-negative rank of a certain matrix associated with the polytope. Okay, so he basically made the job really easy. If you want to prove lower bounds on extension complexity, all you have to do is study this matrix, S of P, that stands for the slack matrix associated with P, and all you have to do is understand its non-negative rank. Okay, so what's the slack matrix? This is the polytope P over here. Okay, and the slack matrix, you have one row for every facet and one column for every vertex, and the entry ij just gives you the distance between the jth vertex and the ith facet. Okay? So it's called the slack matrix because it tells you the slack between every two pairs. And the non-negative rank is just the smallest number of non-negative rank 1 matrices that sum to m. So we've known this since the 90s, and Yannakakis made progress on solving the problem by proving lower bounds for the symmetric case. But it wasn't until 2012 that lower bounds on non-negative rank, and therefore lower bounds on extended formulations for traveling salesmen and clique and other natural NP problems, it wasn't until 2012 that this was fully resolved. And the proof is just information complexity. It uses, like I promised, it's a reduction to set disjointness lower bound. Sorry, set intersection lower bound. I apologize. In the papers, the set intersection problem is called the set disjointness problem. And I'm old school, so I'm going to revert back to that. If I say intersection or disjointness, I mean the same thing. Okay, so how does the proof go? I really wish I could show it to you because it's actually that simple. But basically, you look at they started off by looking at the clique polytope, and they observed more or less, it's not easy to observe because the clique polytope is huge, right? But they more or less observed that the set intersection matrix, our good old set intersection communication matrix, it's actually hiding inside the clique slack matrix. It's just there. If you look at the right vertices and if you look at the right facets, it is the set intersection matrix. Okay, and because of that, they could prove lower bounds on non-negative rank so they follow from information complexity lower bounds for set intersection. Okay, so that gives you a really amazing result that you can't solve clique with a polynomial-sized linear program of this type. And then they used reductions to show that the same thing's true for other NP-complete problems like traveling salesmen and constraint satisfaction problems. And since then, there's been a whole lot of really interesting work extending this, proving stronger results, showing that there's no extended formulations that solve these NP-complete problems, even semi-definite program. You can do the same thing instead of linear programs with semi-definite programs, and you can study their extended formulations. And we now know that, again, these same characters, clique and traveling salesman, we know that these same problems also can't be solved with polynomial size SDP extended formulations. And we have lower bounds on approximation algorithms. Even if you want to approximate the solution with an LP or an SDP extended formulation, you can't do it in polynomial time. Okay, and pretty much all of these results use tools, almost all of them, not all of them, but nearly all of them use the tools of information complexity. Either they use the set intersection lower bound directly, or they use similar ideas to redo the proof. So I think this is a huge success story.
Do these results apply to all NP-complete problems?
No, it's a good question. I mean, they do and they don't. It depends how you formalize your NP-complete problem. So for some formulation, you'll get some results for every NP-complete problem, but it might not be the one that you think is the most natural. Yeah. Because the polytope is independent of the instance, you don't always necessarily get the result that you were looking for.
Aren't there some ways to solve LPs that are actually sublinear in the size of the LP using like a separation oracle?
Yes. That's a good question. I suppose it doesn't directly.
What's the question?
Yeah, so he's saying that you can have an implicit, as long as you have a separation oracle, that you can have more than polynomially many constraints. And what does this have to say? That's a really good question. Yeah, you should work on it. Does anybody know?
I'm sorry, I was going to say a different thing.
Oh, go ahead.
That some of these results also apply to problems which are in polynomial time.
Yes, right.
It's not really about.
Yeah, I'm focusing on the P versus NP question for this talk, but yeah, you're right.
Matching polytope also has required exponential.
Yeah, so we can talk about that later. But yeah, so he's pointing out that there's problems that are solvable in polynomial time with a linear program. This is sort of getting, but doing it this way will not lead to a polynomial time algorithm. Okay, so next, formula-sized lower bounds. So formulas are special types of circuits where the gates, the OR and AND gates, have to have fan-out 1. Okay? And formulas are equivalent, so anything you can compute with a small formula, you can compute it with a shallow Boolean circuit. Okay? So formulas, if you want to prove lower bounds for formula size, it's sort of like trying to understand the parallel complexity of solving the function. Okay, how long does it take you to verify the answer in terms of time if you had parallel processors? Okay, that's one way to think about formulas. And it's a major open problem to prove lower bounds on formula size. So forget about circuits, let's just try for formulas. And formula size has a very nice communication complexity. Proving lower bounds for formula size is equivalent to solving a really nice problem in communication complexity. And this is an old result due to Karshmir and Vigderson. It's not the typical problem that you usually see. It's not a Boolean function the way we're used to it. So let me explain it to you. So the theorem states that the depth of a circuit F is equal to the communication complexity of a corresponding search problem associated with F. And like I said, the depth of a circuit, the optimal depth of a circuit for a function F, that's more or less the same as the formula size. Okay? So what's the search problem associated with the function F? So F it's not a two-player function. It's an ordinary function on n bits. Okay? And the search problem associated with it is you have Alice over here, and she gets an input x that's a 1 of the function. Okay? So if it's the clique problem, she'll be given a graph that contains a clique of size n over 2. And Bob over here is given an input y, and he's given a 0 of the function. So if it's the clique problem, he's given a graph that doesn't have a clique of size n over 2. And their job is just to find some variable xi, some variable where their values on that variable are different. Okay? You know that you can't be a 1 of the function and a 0 of the function at the same time. So there has to be a coordinate where you differ. Okay? And that's the search problem associated with F. Communicate to find such an I. Okay? Simple. And they proved this amazing theorem. It has an easy proof that this is equivalent. So to solve the circuit depth problem, all you have to do is understand this communication problem. And I just want to point out that This is why we like communication complexity so much. You start with a formula, and you want to prove lower bounds on the size of it, and that's related to computation, and you end up with some problem that's about, you know, information transmission back and forth. And it's sort of, you're set up here to sort of try to understand bottlenecks in computation without having to talk about time complexity. Okay, so there's a monotone version of the theorem that restricts attention to monotone circuits. And again, you can show that the best monotone circuit for solving a monotone function f is equal to the communication complexity of the monotone search problem for f. And the only difference is still Alice has a 1 of the function and Bob has a 0, and they're still trying to find a difference. But now we require that the coordinate where they differ, Alice's input is a 1 and Bob's input is a 0. Okay, and if the function's monotone, not only is there a coordinate where they differ, but Alice's is 1 and Bob's is 0. So this is more of a requirement. It's easier to get lower bounds because it's a harder requirement to meet. And it turns out that you can prove lower bounds, again, just a clever reduction to set disjointness lower bounds, and the randomized lower bounds for set disjointness. And it's still open to prove lower bounds for non-monotone circuits. So it's open to make any progress at all on this search problem in the non-monotone case. Okay, since I'm running out of time, I'm going to skip the last application, superlinear circuit lower bounds. We don't even know how to prove lower bounds for general circuits when the size is, you know, 10n and the depth is, or 100n and the depth is logarithmic. And there's connections between circuit lower bounds and a really interesting problem called the rigidity problem in linear algebra, and those are connected to communication complexity as well. I'll skip that. Okay, so just to back up, I gave you some of my favorite applications because they're, you know, lower bound problems. But really, this notion of information complexity, what I presented to you, like it shows here, is just the tip of the iceberg. There's applications to all sorts of areas: streaming, privacy, etc. And I just want to show you in the 1 minute, minus 1 minute that I have left, a really kind of easy, intuitively application to privacy. So differential privacy is a very influential definition of privacy that's been introduced by several people, including Cynthia Dwork, who's here. And I'm going to talk about a two-party version of differential privacy. Okay, so you have a player, Alice, on the left that has a database. Think of the input X as a database. And you have a player, Bob, on the right who has a database. And now you might want to think of this as being a hospital database, and this as being a different hospital in a database. And they want to compute, as before, some joint function of their databases. And now, of course, we don't want anybody in this database. We don't want that guy to learn about any of this stuff, and we don't want this guy to learn about any of this stuff. But the definition of differential privacy is a little different than that. It's saying that if you change a single entry in one of these databases, and you look at the output of this protocol, so it's finally going to output an answer, that the entire transcript, that there's going to be a distribution on transcripts because the protocol is randomized. And differential privacy guarantees you that if you look at the distribution for 2 different hospitals versus the distribution where you change one of the records by just, you just delete, say, one person's record, that the 2 distributions over the whole transcript will be roughly, very close to one another. Okay? So opting in or out of the database doesn't change very much what anybody learns. Okay? And that's the essential definition of what it means for a protocol, a 2-player protocol, to be differentially private. Not only is the output differentially private, but the entire transcript can't reveal, when you change a database by one record, basically what you learn in a distributional setting isn't going to change by much. So this is the formal definition. That is what I said. So you have a protocol P that outputs a distribution of transcripts. And like I said, it's differentially private if when you change Alice's, so you look at a database X and a neighboring database X prime. Neighbor means that you just change one record, that the distribution on transcripts is within a factor of e to the epsilon of pointwise. Okay? And same thing for Bob. And the connection is very simple. So intuitively, you should expect that if you have a protocol that's low information cost, what does that mean? That means you're not you're not revealing too much about your input to the other person. So intuitively, that should mean that you're more private. Okay? And this theorem, that's more like a lemma, it's easy to prove, shows that if indeed you have a protocol P that's differentially private, sorry, I said it the wrong direction a minute ago. If you have a protocol P that's differentially private, then that means you're not revealing too much about any particular input, and therefore you should expect that the protocol will have low information costs. I apologize, I got the order backward. So using this theorem, you can prove, and known lower bounds on information complexity that I've been talking about, you can prove limitations of differential privacy in the two-player setting or multiplayer setting. You can show that there's natural two-party functions that can't be computed differentially privately and maintain low error. Okay. And I'll leave you with that. Thank you very much. In the differential private one? Yeah, so an example is a Hamming distance. So you want to know the Hamming distance between, so just view the database as a 0-1 vector, and you want to compute the Hamming distance between the two. So it is very natural.
I have one more. Does multi-party communication complexity bring in a whole new set of ideas beyond the two-party case?
So there's two versions of multi-party, and I was tempted to talk about them, but I didn't think we would have time. One version, you just have lots of players, and you partition the input into, if you have 5 players, you partition the input into 5 pieces instead of 2, and each player sees just their piece. That's called the number in hand model. And that model, the techniques are quite similar to the two-player case. There's some applications where you need to look at the number in hand, but mostly you get the lower bounds from the two-party. But there's another model which is called number on forehead, where you partition the inputs into those same number of pieces, but each player has their input metaphorically on their forehead. So each player sees all but its own input. So it's a cool model, and it's interesting because every input bit is seen by more than one person, but nobody sees everything. And it's much harder to prove lower bounds in that model, and lower bounds in that model are also connected to circuit complexity.
Thank you very much. Do you want to hear
Thanks.
more about this type of information? Workshop on April 20th.
Yeah, there's going to be some good survey talks on some of this stuff, so if you're interested.